Alright, let's keep going. I'm gonna start the advanced Solidity path now. Solidity. I guess they're gonna add more paths eventually with the coming soon things there. Also, looks like this is a terminal now. In this lesson, we will be covering the theory behind testing Ethereum smart contracts with a focus on truffle, matcha, maca, and chai. Not sure if I'm saying this correctly, but whatever. You need an intermediate. Let me see if I have the stream muted. You need an intermediate level of knowledge of Solidity and JavaScript to help you get the most out of these lessons. If you don't have prior exposure to Solidity or you want to revise some of the concepts, go ahead and start learning with our first lesson. If you're not comfortable with JavaScript, consider going through a tutorial elsewhere before starting this lesson. Let's peep into our project. If you followed along with our previous lessons, you should have built a zombie themed game that is largely ready, and your file structure should look like this. So I have the contracts here and here. Oh, so this is the interface probably. Oh no, JSON. The Oracle stuff, maybe. These parts. And then the contracts here. See the test folder. This is where we are going to be putting our tests. So tests here. Truffle provides supports for tests written in JavaScript and Solidity, but for the scope of this lesson, we're going to keep things simple and stick to JavaScript. Put it to the test. It is best practice to create a separate test file for each contract and give it the name of the smart contract. To create a separate test file. This makes managing your tests simpler in the long run, especially as your project grows and changes. Hi, Ninjak or Ninjak. In the terminal to the right, run touch. So I guess it's running on Linux. Touch test CryptoZombies.js. This is gonna create a file on the task folder. Let's move forward in this chapter. We're going to continue setting things up so we can write and run our tests. Build artifacts. Every time you compile a smart contract, the Solidity compiler generates a JSON file referred to as build artifacts, which contains the binary representation of that contract and saves it in the build contracts folder. Next, when you run a migration, Truffle updates the file with the information related to that network. The first thing you need to do every time you start writing a new test suite is to load the build artifacts of the contract you want to interact with. This way, Truffle will know how to format our function calls in a way that the contract will understand. Let's look at a simple example. Say there was a contract called myAwesomeContract. We could do something like the following to load the build artifacts. So just require the function returns something called a contract abstraction. In a nutshell, a contract abstraction hides the complexity of interacting with Ethereum and provides a convenient JavaScript interface to our Solidity smart contract. We'll be using it in the next chapter. The contract function behind the scenes Truffle adds a thin wrapper around Mocha in order to make testing simpler. Since our course focuses on Ethereum development, we won't be spending much time explaining the bits and bytes of Mocha. If you're inclined to learn more about Mocha, check out our website. Once you're done with this lesson, for now, you only have to understand what we cover here. How to group tests, By calling a function named contract, it extends Mocha describe by providing a list of accounts for testing and doing some cleanup as well. Contract takes two arguments. The first one, a string, must indicate what we are going to test. The second parameter, callback, is where we're going to actually write our tests. Execute them the way we will be doing this is by calling a function named it, which also takes two arguments, a string that describes what the test actually does, and a callback. And I guess this is done in a test net, probably. It's a future-rich JavaScript test framework running on Node.js and in the browser, making synchronous tests simple and fun. I think I stopped here. Execute them. The way we'll be doing this is by calling the function name it, which also takes two arguments, string and a callback. Putting it together is a bare bones test. So I have the contract, the string, which probably is the contract, the name of the contract, and then the callback function, which is what's gonna run, I think. Should be able to receive ithers. Note, a well-taught test explains what the code actually does. Make sure the description of the test suite and the test case can be read together as a coherent statement. It's like you're writing documentation. Every test you want to write follows this simple pattern. CryptoZombies, the first line of code should declare a const named CryptoZombies, and it's gonna require the mock stuff, Mocha, and you set it equal to the result of the artifacts.require function. So it's that artifacts.require, and then CryptoZombies, probably. No. Yeah, I think it's require the name of the contract, probably. Name of the contract we want to test as an argument. Next, go ahead and copy paste the test above. I think I'm gonna write it down just to practice. It's gonna be crypto zombies, then a callback, it should be able to receive ethers. So it also receives a callback. Change the way you're calling contracts such that the first parameter is the name of our smart contract. Note, don't worry about the account segment, we'll explain it in the next chapter. First parameter passed to the it function in our example, that is, should be able to receive ithers, should be the name of our task. Since we'll start with creating a new zombie, make sure that first parameter such you should be able to create a new zombie. There's a typo here, RT. The first task, create a zombie. Before deploying to Ethereum, it is best to test your smart contract locally. You can do so by using a tool called Ganache, which sets up a local Ethereum network. I think I've heard this. I've heard about this tool. Also, this is part of Truffle, I think. Every time Ganesh starts, it creates 10 tasks accounts and give them 100 ethers to make testing easier. Since Ganache and Truffle are tightly integrated, we can access these accounts through the accounts array we've mentioned in the previous chapter. But using accounts 0 and accounts 1 would not make our test readable. To aid comprehension, we'd like to use two placeholder names, Alice and Bob. So inside the contract function, let's initialize them like so. So inside the contract, so here. Let's Alice Bob equals accounts. Don't forget the programmer, JavaScript. Okay, so while Alice and Bob, there is a big tradition that makes Alice and Bob, or A and B, common names used in cryptography, physics, programming, and more. It's a short but interesting history and well worth it. Say Alice wants to play our awesome game. If so, the first thing you would want to do is create her own zombie. To do that, the front end, or truffle in our case, would have to call the create random zombie function. Note as a review, here's the Solidity code and contract. We begin by testing this function. Put it to the test. We would want to properly call the it function. The second parameter, callback function, is going to talk to the blockchain. So replace true and true. True and true, replace the first parameter and make the callback async. Which means that the function is asynchronous. Just prepend the async keyword. So I guess it's here that it comes, async. This way, every time this function gets called with the await keyword, our test waits for it to return. Explaining how promises work is out of the scope of this lesson. Once we've finished this lesson, feel free to check out official documentation. Oh, so it's just that. Usually every test has the following phases: setup, in which we define the initial state and initialize the inputs; act, where we actually test the code. Always make sure you test only one thing; assert, where we check the results. Let's look at what our test should do in some more detail. Chapter 2, we learn to create a contract abstraction. However, a contract abstraction, as its name says, is just an abstraction. In order to actually interact with our smart contract, we have to create a JavaScript object to act as an instance of the contract. Continue our example with my awesome contract. We can use the contract abstraction to initialize our instance like this. Good, so what's next? So it's probably gonna initialize here the instance of the contract. And it uses await because of the async of the callback function. So this is gonna return a response. This is a resolve, I think. The response after the async call. Calling create random zombie requires us to pass it the zombie's name as a parameter. So I think it's gonna be await then create random zombie .new. Probably. So the next step would be to give a name to Alice's zombie, something like Alice's awesome zombie. However, if we do this for each task, our code is not going to look pretty. A better approach is to initialize a global array as follows. And then call the contracts methods like so. So first initialize the name with the zombies, the array of the zombies. Call contracts methods like this. Contract instance that create a random zombie. And then the name. Note using an array to store zombies names comes in handy if you want, for example, to write a task that creates 1,000 zombies instead of just 1 or 2. We've gone ahead and initialized the zombie names array for you. And so it's outside of here. Let's create an instance of our contract, declare a new const contract instance equals true await. And set it equal to CryptoZombies dot new function. And then I have to pass the zombie names, I think. Oh, it's not saying that I have to, so. Oh, it's just when you're. Yeah, it's not here. Here is just creating an instance of the contract, and then you're gonna use the contract to call the function inside of the contract. So we've reached the part where we're going to be calling the functions that create a new zombie for Alice, but there's a slight problem. How can we make it so the method knows who calls it? Another way to put it would be, how can we make sure Alice and not Bob is going to be the owner of this new zombie? Well, the problem is solved with the contract abstraction. One of the features of Truffle is that it wraps the original Solidity implementation and lets us specify the address that makes the function call by passing that address as an argument. The following calls create random zombie make sure message.sender is set to Alice's address. Now I have a quick question for you. Do you know what gets stored in result? Well, let me explain. So it's gonna be the return of the function, I think. Once we specify the contract we want to test using artifacts that require, Truffle automatically provides the logs generated by our smart contract. What this means is that we can now retrieve the name of Alice's newly created zombie using something like result.log0.args.name. In a similar fashion, we can get the ID and the DNA. Besides these bits of information, result is going to be giving us several other useful details about the transaction. Result.tx, the transaction hash. Result.receipt, an object containing the transaction receipt. If result.receipt.status is equal to true, it means that the transaction was successful. Otherwise, it means that the transaction failed. Note that logs can also be used as a much cheaper option to store data. The downside is that they can't be accessed from within the smart contract itself. Assert. In this chapter, we will be using the built-in assertion module, which comes with a set of assertion functions such as equal and deep equal. Simply put, these functions check the condition and throw an error if the result is not as expected. Since we will be comparing the simple values, we are going to be running assert.equal. Put it to the task. Let's finish our first task. Declare const name result and set it equal to the result of contract.instance contract instance dot create random zombie with the zombie's name and the owners as arguments. So zombie names 0, or maybe just zombie names. Yeah, I'm not sure if I can pass the two at the same time. And then the second one is message.sender, but I think there's from message.sender. Or accounts, actually. Accounts, yeah, but then I have to choose which one. It can't be message.sender because I'm on the JavaScript file, not Solidity. So that should be accounts. Next line, check if, okay. I think it stops here. Set equal to result of this random zombie, another arguments. once we have the result, call assert.equal with two arguments. Result.receive.status and true. So I think I'm just gonna choose one of them. Counts 0. But I'm not sure if I'm supposed to do that. Assert.equal. Result.receive status true. If the above condition is true, we can assume that our test has been passed. Just to be safe, let's add one more check while we are here. In the next line, check if result.logs target name equals is assert equal args.name is equal to zombie names 0. Yeah, so I'm probably gonna have to pass 0 here. Now it's time to run truffle tests. Yeah, I think because the function create random zombie only accepts one zombie at a time. Now it's time to run truffle tests and see if our test passes. The way this works is that truffle will just inspect the test directory and execute the files it finds there. Actually, we've gone ahead and did that for you. The output should look something like this. This includes your very first task. Also, I just need to pass it like this instead, actually. So maybe I did something wrong here. Zombie names 0. Oh. Oh, it's here probably. Yeah, cert. So now I need to change this. So I think here is just Alice. Yeah, I don't really understand what accounts is, actually. It's still incorrect. Contracts instance dot create random zombie names from Alice. So that should be the name, the from state. If this from is not required. It's set to Alice's address. So here's making Alice and Bob equals to accounts. So maybe accounts.alice or accounts. Yeah, but I don't think that. Yeah, it's probably not this. Doesn't make sense. Maybe it's the zombies? Yeah, I have no idea. I'm gonna have to look at the solution, I think. So I have the result, cost, third equal of two arguments. Result dot set the status. And this one seems to be fine. Result logs dot name. So what am I missing here? Zombie name 0. Now it's time to run truffle test. Yeah, I don't see what's wrong here. Oh, so it's just the comma? It's weird because here it was working with the comma. With the space through the comma. And here, well, maybe it's just the comma as well, I think. No. Yeah. Just this is probably not gonna work as well. I'm gonna look. So what's different than what I was doing before? Oh, I forgot they will wait. That's why. That's the problem. Awesome work so far. Now we know for sure our users can create new zombies. However, if they could keep calling this function so to create unlimited zombies in their army, the game wouldn't be very fun. Thus, in chapter 4, we've added required statements to create zombies. Just a few minutes, we will have more than one task, and the way this works is that each task should start with a clean sheet. Thus, for every single task, we'll have to create a new instance of our smart contract like so. So, contract instance await CryptoZombie news. Wouldn't it be nice if you could write this just once and have Truffle run it automatically for every task? Well, one of Maka's and Truffle's features is the ability to have some snippets of code called hooks run before or after a task. To run something before a task gets executed, the code should be put inside a function named before each. So instead of writing contract new several times, you just do it once like this. Then Truffle will take care of everything. That's pretty sweet, isn't it? Not sure if I get this, but put it to the test. Load the line of code that initializes Alice and Bob also here. So probably I need to use this before each. You want contract instance should be limited in scope to the block in which it's defined. It's the last instead of var. Yeah. Contract instance. Next, copy and paste the snippet from above for defining the before each. So I sync. Let's fill in the body of our new function. Go ahead and move the line of code that creates a new contract instance instead of the bar before each function. Now that we've defined contract instance somewhere else, you can remove the const qualifier. So this is going to create a new contract instance for each task. But I wonder why it goes after this each one here. Let's fill in the body of our new function. Go ahead. Oh, that's defined. Okay. We're going to want a new empty eat function for our task. Set the name of the task. That is the first parameter we're passing to the eat function. Equal to should not allow CryptoZombies. I'm just gonna copy this. Should not allow CryptoZombies. I think here I have to put this and this probably. If you really want to achieve mastery, go ahead and read on. Otherwise, just click next and off you go to the next chapter. After all, why would you want to deny yourself a whole lot of us? Let's circle back to how contract.new works. Basically, every time we call this function, Truffle makes it so that a new contract gets deployed. On one side, this is helpful because it lets us start each task with a clean sheet. On the other side, if everybody would create countless contracts, the blockchain would become bloated. We want you to hang around, but not your old task contracts. We would want to prevent this from happening. Happily, the solution is pretty straightforward. Our contract should self-destruct once it's no longer needed. The way this works is as follows. First, we would want to add a new function to the CryptoZombies smart contract like so. Note if you want to learn more about self-destruct, you can read the Solidity docs here. The most important thing to bear in mind is that self-destruct is the only way for code at a certain address to be removed from the blockchain. This makes it a pretty important feature. Next, somewhat similar to the before each function explained above, we'll make a function called after each. Lastly, Truffle will make sure this function is called after a task gets executed. And voila, the smart contract removed itself. We have a lot of ground to cover in this lesson. Implementing this feature will likely require at least 2 additional chapters, so we trust you to add it. So do I need to put this here? I'm not gonna put it actually. But I think I understand what they mean by that. So here probably I can remove this. And I probably typed something wrong. Before each. Async. So what is wrong here? Find the new int function. Oh, I need to put Also makes more sense. So I need to put this here actually, probably. And then here I defined the new int function. But I'm still getting the mistake here. Should probably. Probably that's it. Yeah, there we go. This chapter we're going to fill in the body of our second task. Here's what I should do. First, Alice should call create random zombie, give it zombies names, 0 as the name of her first zombie. Next, Alice should try to create her second zombie. The only thing that's different is that this time the zombie name should be set to zombie names 1. At this point, we expect the contract to throw an error. This our test should pass only if the smart contract errors out. Our logic will look a bit different. We have to wrap the second create random zombie function call instead of a try catch block as follows. Now we've got exactly what we wanted. Pretty close, but not quite there. Use, okay. This is how the line of code that calls the function should look like. Put it through the task, the previous we create empty shell. First, let's have Alice create her first zombie, give it zombie names, 0 as a name, and don't forget to properly set the owner. Just probably contract instance dot create random zombie. This should be the same as this one. After Alice created her first zombie, run should throw. We create random zombie as a parameter. So it's probably this. Oh wait. Tools don't should throw. If you can't remember the syntax for doing this, check the example above. Awesome, we've just finished writing our second task. Okay, so let's see if this. Maybe we should put results in the second one and should throw is incorrect, I think. Yeah, but it's still giving me a mistake there. Because it should be passing an argument. So maybe I should put result, but maybe if I put a different name. Or maybe just await then. Contract instance. And maybe that's the way. And now I have to fix this one. Yeah, I don't understand. I don't see what I'm doing wrong here. Maybe if I take this off, probably not gonna work. And if I do it like this, it doesn't make sense. Maybe I should do in one line. Let me see. Yeah, I don't get it. Also, this part is not that interesting to me, to be honest. I was much more interested in the chain link stuff. If you've been following along with the previous lessons, you should know that amongst other things, our zombies in art from USC 721, this has two different ways to transfer tokens. The first way is Alice, the owner, calling transfer from with her address as a from parameter, Bob's address as true parameter. Wants to transfer. The second way is Alice first calling approve with Bob's address and the zombie ID. The contract then stores that Bobby is approved to take the zombie. Next, when Alice or Bob calls transfer from, the contract checks if that message that sender is equal to Alice's or Bob's address. So if so, it transfers the zombie to Bob. We'll call these two ways of transferring zombies scenarios. In order to test each scenario, we would want to create two different groups of tasks and give them meaningful descriptions. By group then, we only have a few tasks. Yes, right now our logic is pretty straightforward, but this might not always be the case. Still, the second scenario, that is approve followed by transfer from, requires at least two tasks. First, we must check if Alice herself is able to transfer the zombie. Second, we also have to check if Bob is allowed to run transfer from. Moreover, in the future, you might want to add other functionalities that will require different tasks. We believe it is best to put a scalable structure in place from the very beginning. It makes understanding your code much easier for outsiders or for yourself if you spend time concentrating on something else for a little while. Yeah, I think I'm not gonna spend a lot of time on this, to be honest. Yeah, but maybe I should. I'm not sure. Because writing the stats is something that I never do. I've never done so far, even with normal programs. I think it's just a lot easier and more practical to do console logs and use the debugger instead to figure out what's wrong with the code instead of or just simply thinking about it instead of running tasks. I'll close the window a little bit. To group tasks, Truffle provides a function called context. Let me quickly show you how we use it in order to better structure our code. So context If we add this to our CryptoZombies.js file and then run truffle tasks, the output will look similar to this. Take a look again, there's an issue with the above output. It looks like all tests have passed, which is obviously false since we didn't even write them yet. Fortunately, there's an easy solution if you just place an X in front of the context. Function as follows. Truffle will skip those tasks. Note, X can be placed in front of a eat function as well. Don't forget to remove all the X's when the tasks for those functions have been written. Now let's run truffle tasks. The output should look something like this. Where represents maker. Go ahead and copy paste the code from above. Let's assume this one. So I assume is this. It's telling me to copy. But I'm not sure. Probably need to put that X here. So far, we've merely been warming up, but now it's time to really show off what you know. Next chapters. Should create a new zombie. The first line of the function. Honestly, this is not interesting to me. I'm thinking about skipping this part, actually. I think I'm more interested in one, how the chain link works, how to deploy contracts on different different protocols, and seeing the source code of other projects probably will help me understand better how it works. And also how to bridge the gap there. If I want to use Python for some things and JavaScript for other things, how to do that. And then obviously the payable stuff, pay and receive, which was already talked about here briefly. But I want to know the best practices, and also probably investigate how to investigate source code from other contracts. I think that's important as well. The first line of the function should call create random zombie, give it zombie names as the name, and make sure LSA is the owner. I think I'm just gonna skip these ones. I'm just gonna read and see the solution actually. Until I get through some part that I think is more interesting to me. Now the approve followed by transfer from token is far from being a walk in the park. Alice approves Bob. Yeah, if this is important, then I'll probably have to figure out eventually whenever I'm trying to build projects how to use this stuff again, and then I'm probably gonna learn better. Difference in the two scenarios, like if who calls the actual transfer, as above, we made it look simple. Mob calls transfer form. For these scenarios as follow. Alice creates a new token. Call cert.equal if no owner. It's a code. I could paste that for you. Yeah, whatever. So probably have to erase this one. Close to being done with testing the transfers. Let's now test the scenario in which Alice calls transfer form. I have some good news for you. This test is straightforward. All you have to do is copy and paste. Code from the previous ones. So I guess it's the last one here. The previous chapter were pretty informative, information dense, but we covered a lot of ground. So why are we done now with all the scenarios? No, we're not there yet. We've left the best stuff for the end. We've built a zombie game, and the best part is where zombies fight each other. This test is pretty straightforward and consists of the following steps. We're going to be creating two new zombies, one for Alice and the other one for Bob. Second, Alice will run an attack on our zombie with Bob's zombie ID as a parameter. Finally, for the test to pass, we're going to check if results received status equals true. While we're here, let's say I've quickly coded all this logic, wrapped in an it function and run truffle tasks. Let's figure out first, grand zombies. I think this is probably stuff that you get. It's better to learn by actually doing as well. I wanna know if they're gonna talk about deploying the contract. I'm not sure if they did already and I didn't understand or forget. Our test failed because we added a cooldown period to our game. It made it so zombies have to wait 1 day after attacking or feeding to attack again. Without this, the zombie could attack and multiply countless times per day, which would make the game much easier. Now, what should we do now? Per day, time traveling. EVM increase time increases the time for the next block. EVM mines a new block. In fact, there's no need to wait at all. That's because Ganesh provides a way to move forward in time through helper functions. Let me explain how these functions work. Yeah, blah, blah, blah. Another thing that I'm interested in is understanding how miners get to mine the blocks, how the whole thing works. Because I know that you can have algorithms to mine blocks, and you have mining pools, but I'm not sure how they build the algorithms. So that could be interesting as well to research. We're gonna add and move everything to a new file named helpers time.js to increase the time. You simply have to call time increase time. It's still not good enough after all. Do we really expect you to know how many seconds are there in a day? Of course not. This is why I had helper functions. So time, days, well. Obviously time traveling is not available on the mainnet or at the subtestnet. Scroll down in the comments. You're just gonna look at the solution. It's probably gonna be here. More expressive assertions with chai. Until now, we've been using debuting assert module to write our assertions. While not bad, the assert module has a major drawback. The code doesn't read well. Unfortunately, there are several rare assertions. Chai is very powerful, and for the scope of this lesson, we're just going to scratch the surface. Once you finish this lesson, feel free to check out their guide to further your knowledge. Let's take a look at the three kinds of assertion styles bundled into Chai. I think I've seen some stuff about this Chai library on FreeCodeCamp for Node.js. It's probably similar to that. If not the same library, actually. Yeah, whatever. So maybe I need to erase this, sure. So which line is it? Maybe I can just copy the whole thing actually. It's easier. Impressive, Now the tutorial would not be completed without showing you how I should test again Loom testnet. Apart from our previous lessons that on Loom users have access to much speedier and gas-free transactions than on Ethereum. This makes dApp chains a much better fit for something like a game or a user-facing dApp. Deploying and testing against Loom is not different at all. We've gone ahead and summed up what needs to be done so we can test against Loom. Figure truffle for testing on Loom. First things first, let's tell truffle how to deploy to Loom testnet by placing the following snippet inside the network's object. Never review your private key. We're only doing this for the sake of simplicity. A much safer solution would be to save your private key into a file, read its value from that file. If you do this, make sure you avoid pushing the file in which you saved your private key to GitHub. The accounts array, in order to make Truffle talk to Loom, we've replaced the default HD wallet provider with our own Truffle provider. As a result, we have to tell our provider to fill in the accounts array so we can test our game. In order to do that, we are required to replace the line of code that returns a new Loom Truffle provider. So I guess Truffle is a provider as well. Finish the task, replace the line of code that returns a new Loom Truffle provider with the snippet from above. Object with configuration for each network. So it's using a different provider. It's using inferior. And then using Truffle to connect to the provider, I think. This one I think you should take care of. Time traveling is only available when testing against Ganache, so we should skip this task. We already know how to skip tasks by placing an X in front of the function name. However, this time we want you to learn something new, long story short. We can skip a task by simply chaining a skip function call as follows. We've gone ahead and skipped the task for you, then we run truffle task. So I'm not sure what I'm supposed to do here. So replace this one with this. So creates a constant equal to the provider. Then uses this create extra counts from mnemonic. Okay, so now it's gonna talk about deployment. And then this from the third part should be more interesting, I think. If you're new to CryptoZombies, it's highly recommended to go over the first 6 lessons before starting this one. So you've worked your way through our previous lessons, awesome. This means you've almost mastered the art of building the apps. But an important piece of the puzzle is still missing. Still have to learn how to deploy a smart contract. Now if you have a background in front-end development, you're probably well accustomed to the multitude of tools like Webpack, Gulp, or Browserify that make a developer's life simpler. But what tools do Solidity developers use? Truffle is the most popular blockchain development framework for good reason. It's packed with lots of useful features. Easy smart contract compilation, automated API generation, integrated smart contract testing. There's even support for Mocha and Chai. Support for multiple networks. Code can be deployed to RinkBuy, Ethereum, or even Chulum. So just these three. We'll walk you through this later. Provided that npm. So I think I can search for this later actually. Frameworks for deploying smart contracts, probably. Provided the npm and node have been installed on your computer, we want you to install Truffle and make it available globally. Yeah, so I guess there are these ones actually. You can probably use Remix to deploy on other. Yeah, I'm gonna search for that. I wanna deploy contracts on the Polygon network because it's cheaper, a lot cheaper than Ethereum mainnet. So that's the one I'm gonna look for after I do this stuff. We start with the basics, fire up a new terminal window, create a directory called CryptoZombies and cd into it. So I'm not sure if I should do this or if they're telling me to do it here. Or maybe here I just do npm. I'm gonna try to create the directory and see what happens. And so I'm probably just need to npm install. It doesn't make a lot of sense to create a directory here on this terminal. Oh, it's probably npm install profile. Now that we've installed Truffle, it's time to initialize our new project burning Truffle init. All it is doing is to create a set of folders and config files with the following structure. So contracts, migrations. This is pretty complicated. Don't worry, learning to use Truffle won't teach your brains. Walk it through stuff. So running the truffle init command inside of the CryptoZombies directory should create several directories and some JavaScript and Solidity files. Let's have a closer look. Contracts. This is the place where Truffle expects to find all our smart contracts. To keep the code organized, we can even create nested folders such as contracts tokens. Now, Truffle init should automatically create a contract called migrations.sol and the corresponding migration file. Explain them a bit later. I've seen migrations on Django, and as far as I understand, I'm not actually really sure, but I think it's for the database stuff. I don't remember really well how it works. From Django, I think it creates database models whenever you use make migrations or something like that. And then updates the views and URL paths. But I don't really know that well. A migration is a JavaScript file that tells Truffle how to deploy a smart contract. So I guess it's pretty much the same concept, but instead of a database, is creating the rules for deploying on the blockchain instead. And whenever you have the Django project, is creating the rules to deploy on a server, creating the URL links, URL routes, and the database models. Here we are expected to put the unit tests, which will be JavaScript or Solidity files. Remember, once a contract is deployed, it can't be changed, making it essential that we test our smart contract before we deploy them. Truffle.js and Truffle config.js. Config files used to store the network settings for the deployment. Truffle needs two config files because on Windows having both Truffle.js and Truffle.x, the same folder might generate conflicts. Long story short, if you're running Windows, it is advised to delete Truffle.js and use Truffle config.js as the default config file. But why should I use the directory structure? I'm not used to it and it looks complicated. There's a few good reasons. First, Truffle will not work as expected if you change the names of these folders. Second, by adhering to this convention, your projects will be easily understood by other developers. Using a standard folder structure and code convention makes it easier. Yeah, this is normal, I think. Truffle HD wallet provider. In this lesson, we will be using Infura to deploy our code through Ethereum. This way, we can run the application without needing to set up our own Ethereum node or wallet. However, to keep things secure, Infura does not manage the private keys, which means it can't sign transactions on our behalf. Since deploying a smart contract requires Truffle to sign transactions, we are going to need a tool called Truffle HD Wallet Provider. Its only purpose is to handle the transaction signings. Maybe you're asking why we chose not to install truffle, which the wallet provided in the previous chapter, and something like npm truffle. Well, the truffle init command expects to find an empty directory. If there's any file there, it will error out. Thus we need to do everything in the correct order, install truffle, and run truffle init. So truffle init, and then npm install truffle HD wallet provider. So maybe it's worth it to copy this stuff for the future. Just making sure that I understand what's going on before moving. So I guess that truffle uses Infura, which is the provider, which is the bridge between the blockchain and the application, because Infura is connected to is listening to events and reading and writing data to the blockchain. And the alternative would be to create your own node, which is not incentivized to do, because if you want to create a full node, it probably takes weeks to set it up, because of the amount of data in the blockchain. Unless you want to create a light node, then you probably don't have the full spectrum of functions or things you can do. So you use Truffle, the framework, to deploy, which is kind of like Django, but for Solidity instead. I think I get it so far. Now that we've put the project structure in place and set up Truffle HD wallet provider, let's compile our contracts. The Ethereum virtual machine can't directly understand Solidity, thus we need to run translate. Okay, this we already know. Using the Solidity compiler. Now that we're talking about the Solidity compiler, we should mention that the DAOs managed to bake in some nifty features. Let's pretend we want to modify the definition of the add function included in SafeMap. If we're going to compile this function, the Solidity compiler will throw a warning. Super. What the compiler is trying to say is that our function does not read or write from to the blockchain, and that we should use the pure modifier. While making the function pure, our view saves us gas. Since these functions are not going to modify the state of the blockchain, there's no need for miners to execute them. To put it in a few words, pure and view functions can be called for free. Remember, we've embedded our logic in a smart contract called zombie ownership.sol. Not a great name for a game. Fortunately, this isn't a problem. We can use inheritance to create a smart contract with the same actions and features with whatever name we choose. Let's create a new smart contract named CryptoZombies that inherits from zombie ownership.sol. Next, we copy all our smart contracts into the contracts folder. Now the project structure should look like this. Everything set up properly. Let's compile our project. Execute truffle compile. This command should create the build artifacts and place them in the build contracts directory. So the way you compile is truffle compile. So I'm gonna write here truffle compile. Build artifacts are comprised of the bytecode versions of the smart contracts, ABIs, and some internal data Truffle is using to correctly deploy the code. Avoid editing these files or Truffle might stop working correctly. Normally at this point, before deploying to Ethereum, you would want to test your smart contracts locally. You can do this using a tool called Ganache, which sets up a local Ethereum network. However, while testing is very important, it requires an entire lesson to cover. So we're just going to stick to deployment in this lesson. If you're so inclined to learn more about testing, I recommend our very own Testing Smart Contracts with Truffle lesson. Oh, it's the one that I did already. But I don't remember seeing them talk about this Ganache. I think they talked about the functions, how to make the different assertions, but yeah, whatever. I'll look into it later if I need it. To deploy to Ethereum, we will have to create something called a migration. Migrations are JavaScript files that help Truffle deploy the code to Ethereum. Note that Truffle Init created a special contract called migrations.sol that keeps track of the changes you're making to your code. The way it works is that the history of changes is saved on chain. Thus, there's no way you will ever deploy the same code twice. We'll start from the file Truffle Init already created for us. Let's take a look at what's inside. So var migrations artifacts require migrations.sol. Then it's exporting this function deployer. First, the script tells us Truffle that we'd want to interact with the migrations contract. Next, it exports a function that accepts an object called deployer as a parameter. This object acts as an interface between you, the developer, and Truffle's deployment engine. Even though the deployer provides a multitude of useful functions, we won't be using them in the scope of this lesson. Once we've finished, feel free to check out Truffle's documentation if you're inclined to learn more about Truffle's abilities. To get everything ready for deployment, we've gone ahead and created a new file and copied and pasted the content from this. Put it to the task, modify this file to this. So var CryptoZombies function deploy CryptoZombies. And put a new song. Awesome, you've successfully compiled the source code and created a migration file. There's still one more thing to do before you can deploy. I've shared the configuration file to tell Truffle the networks we want to deploy to. I thought there was only one Ethereum network, what am I missing here? Several public Ethereum test networks let you test your contracts for free before you deploy them to the mainnet. Remember, once you deploy a contract to the mainnet, it can't be altered. These test networks use a different consensus algorithm to the mainnet, usually proof of A? I don't know what POA is. And Ether is free to encourage through thorough testing. I don't know what this is proof of what. In this lesson, we will be using RinkBuy, a public test network created by the Ethereum Foundation. The truffle.js configuration file. Now let's take a look at the default truffle configuration file. It is just an empty shell. Thus, we'll be required to update this file to allow us to deploy contracts through RinkBuy and the Ethereum mainnet. So I have the mainnet provider, this HD wallet provider. Remember the second chapter, we asked you to install an additional package called Truffle HD wallet provider. Sign transactions. Now we want to edit our configuration file and choose HD wallet provider. To get this to work, we'll add a line at the top of the file. So just requiring the provider. Create a new variable to store mnemonic. Note that we don't recommend storing secrets like a mnemonic or a private key in a configuration file. Config files are often pushed to GitHub where anyone can see them, leaving you wide open to attack. To avoid revealing your mnemonic or your private key, you should read this from a file and add that file to gitignore. We'll show you how to do this later. So I don't understand really well what's mnemonic. What is that? I guess it's the private key, but to keep things simple, in this case, we'll copy the mnemonic and store it in the variable. Set up Truffle for RinkBuy and Ethereum mainnet. Next, make sure Truffle knows that the network we want to deploy to will have to create two separate objects, one for RinkBuy and the other one for the Ethereum mainnet. So just specify the name here. Return new HD wallet provider. And then there's a different inferior address. Var value is wrapped up in a function which ensures that it won't get initialized until it's needed. Wrapping it up, now let's put these pieces together and have a look at how our config file should look. So first initialize the wallet, the mnemonic, the module that exports and exports the objects with the networks. Thus, we're gonna add and updated most of the configuration file for you. Let's fill in the missing pieces at the top of the file, add the code, Truffle provider, fill in the network ID for the RinkBuy network. If you can't remember the value of this parameter, check the code snippet from above. I'm not sure. Also, it's 4. And it should be wrapped in strings. Or maybe not, actually. So it shouldn't. And here I also did something wrong. Acquire Truffle HD wallet provider. Oh, it has to be const. That's the problem. So maybe if I erase this comment, yeah, there we go. Deploying our smart contract, great. That was the difficult part. Actually, deploying to RinkBuy is going to be straightforward to do. To do this, Truffle relies on something called a migration. It sounds like a migration involves a lot of stuff moving around, but in practice, a migration is nothing more than a JavaScript file that tells Truffle how to modify the state of our smart contracts. Obviously, the first migration will just deploy the smart contract. Some other migrations deploy a new version of the code to add features or fix bugs. In a nutshell, migrations provide a convenient way to keep track of the changes you make to your code. If you want to deploy more than one contract, a separate migration file must be created for each contract. Migrations are always executed in order. This lesson will deploy only to Rinkby. Deployment to the mainnet will require real money to pay for the gas, and once deployed, we won't be able to modify the code. Hence, it's best to deploy to the Rinkby first and thirdly, I don't know how to say this word. That's the code. Get some Ether. Before doing the deployment, make sure there is enough Ether in your account. The easiest way to get Ether for testing purposes is through a service known as Faucet. Recommend the authenticated faucet running on Rinkby. Following the instructions and within a few minutes, your address will be credited with some Ether. And that's the problem with doing this on stream, I think. Because I don't think I can do unless I create a wallet just for this, which I think I might do actually. Just create a new wallet just to do these things on stream. It's running on the Rinkby network to prevent malicious actors from exhausting all available funds of Ether through month-long running spam attacks. Also, you need to request either through Twitter or Facebook. Or maybe just put the address of the MetaMask. Now that everything is set up, it's time to deploy Rinkby into the soul run. Truffle migrate network Rinkby. Truffle deploy is just an alias for truffle migrate. However, since our command line interpreter is pretty basic, it won't consider the answer correct unless you're using migrate. So truffle deploy and migrate's the same thing. Deployment to the mainnet is not complicated at all. Once the smart contract is tested, you only have to run truffle migrate network mainnet. Don't forget that you have to pay for gas with trust to be able to do it. If everything goes well, you're going to see a response that's similar to the one to the right. So I guess you can use this to deploy on Polygon, but I'm not really sure. Because maybe not, because the options they give there didn't include Polygon. It might not seem much, but you just apply the CryptoZombies smart contract. Loan base chain. Now, if you want to build dApps on Ethereum, there's one thing you should be aware of. On the mainnet, users are required to pay a gas fee for every transaction, but this isn't ideal for a user-facing dApp or a game. It can easily ruin the user experience. Conversely, on Loom, your users can have much speedier and gas fee-free transactions, making it a much better fit for games and other non-financial applications. This means that your Loom zombies will be fast zombies. That's not all. Deploying to Loom is not no different from deploying to RinkBuy or to the Ethereum mainnet. If you know how to do one, you also know how to do the other. The next chapters will be walking you through deploying to Loom. On Truffle Provider. We at Loom are using Truffle to build tasks and deploy our smart contracts. To make our life easier, we developed something called the provider that lets Truffle deploy to Loom, just like it deploys RinkBuy or Ethereum mainnet. Without delving too much into details, the provider works like a bridge that makes Web3 calls compatible with Loom. The beauty of it is that to use it, you don't have to understand how it works under the hood. Middle Truffle then a PEM package. This time, there's no need to make the package available globally. So, npm install Truffle provider. This chapter, we're going to deploy our smart contract to the Loom testnet, but before doing the development, some prep work is needed. First, we should create our own Loom private key. The easiest way to do it is by downloading and installing Loom according to this store. Next, create a private key is as simple as this. So you just run the commands and then you type in the stuff. Type in the address. Never review our private keys. We're only doing this for simplicity's sake. The first thing we are required to do is to initialize Loom Truffle provider. This syntax is similar to the one we've already used for HD wallet. So here. Next, just as we did in chapter 5, we will have to let Truffle know how to deploy on Loom testnet. Let's add a new object to Truffle. So is inside the networks object, and it's just the new one. Specifying specifying the nets. Then the provider is the function which contains the stuff. It's slightly different because it has more things inside of the function. Yeah, but pretty much the same logic. Add the line code, place the configuration. Run Truffle migrate network Loom testnet and check the output. So Truffle migrate network Loom testnet. So now I'm thinking that it might be possible to just use Truffle to deploy with Polygon. You just need to change the provider, and you do the same process probably. Because then you specify the network. It's gonna be a different provider, and you just put the function there. Deploy to base chain. Congratulations, you've successfully deployed to Luna testnet, but can you guess what's coming next? This chapter will walk you through the process of deploying to base chain, that is our mainnet. Here's a brief rundown of what you do in the start. Create a private key. You already know how to create a private key, however you must change the name of the file if you're going to save it. Securely pass the private key to Truffle. So create a git ignore and append the private key to this. Now that we made sure secrets aren't going to be pushed on GitHub, we must edit truffle.js configuration file and make it so that the truffle is the private key from this file. So it adds these things. Tell truffle how to deploy each base chain. This is pretty much the same thing that I did for the previous ones. At least your deployment keys before deploying to base chain. I'm sure I'm probably gonna have to review this stuff because I'm not gonna remember how to do this exactly the way that it is here. You need to whitelist your keys by following the instructions for deployment mainnet guide. Run truffle migrate. So I think this is probably the last lesson on this one. Yeah. So now things should get more interesting, I think. Setting things up. Before we begin, let's be clear, this is an intermediate lesson. It requires a bit of JavaScript and Solidity knowledge. Okay. Now let's suppose you're building a DeFi app and want to give your users the ability to withdraw Ethereum or for a certain amount of USD. To fulfill this request, your smart contract, for simplicity's sake, we'll call our contract from here on. Must know how much one Ether is worth. And here's the thing, a JavaScript application can easily fetch this kind of information and making requests to the Binance public API. I think it's the same thing that was already said in previous lessons. Now I know the picture is something so here's a simple diagram. So I have the user calls a function of your smart contract, call your smart contract, validates the response, updates the Ethereum price, and continues processing. Response to the request. So the flow is this. So request the latest Ethereum pricing, Ethereum price for Oracle smart contracts, send the request, associated request, Node.js Oracle service, Binance public API. So it is getting the price from Binance, but it's passing through the Oracle first, I think. Let this sink in before I read on. For now, let's initialize our new project. So but a smart contract can't directly access data from the outside world, so it relies on Oracle to pull the data. Also, I guess both Binance and the client gets from the Oracle in this. Fire up terminal window and move into your project directory, then create a directory called Ethereum price Oracle and stage. In the box to the right, initialize your new project by running the pm init y command. Next, let's install the following dependencies: truffle, open, zapling, solidity, long.js, long-truffle, provider bin, .js, and Nexus. You can install multiple packages by running something like the following. Why do you need all these packages, you ask? Read on and things will become clearer. You'll be using Truffle to compile and deploy your smart contracts to Loom testnet, so we've gone ahead and created two bare bones Truffle projects. The Oracle will live in the Oracle directory. So let me see. I think, yeah, I have to do this one by one. So I'm probably gonna do this one first. Truffle, open, zapling, solidity, Loom.js, Loom, truffle, provider, pn. I'm not sure if I should write it like this. So I'm getting an error here. I guess it's just, yeah. If I install one by one, it's better. Complying the player smart contracts, so we've gone ahead and created two bare bones truffle projects. The Oracle will live in the Oracle directory. The caller contract will live in the caller directory. We trust you to do the same, and if everything goes well, your directory structure looks like something like the following. So I probably don't need to do this, to install this stuff for those. So 3 L2 node modules. So I have the caller contract stuff. And each of these are a folder, I suppose. Yeah, the folder of the contracts, migrations, and tasks. Learning how to use Truffle is beyond the scope of this lesson. If you're inclined to learn more, check the applying apps. Okay. So apparently I do need, I need to do npm init first. Now I do the stuff there. Calling other contracts. Now instead of jumping directly into the Oracle smart contract, we will continue by looking into the caller smart contract. This is to help you understand the process from start to finish. One of the things the caller smart contract does is to interact with the Oracle. Let's see how we can do this. For the caller smart contract to interact with the Oracle, you must provide it with the following bits of information: the address of the Oracle smart contract, the signature of the function you want to call. I reckon that the simplest approach would be to just hardcore the address of the Oracle smart contract. But let's put on our blockchain developer hat and try to figure out if this is what we want to do. The answer has to do with how the blockchain works, meaning that once a contract is deployed, there's no way you can update it. As the native calls it, contracts are immutable. If you think about it, you'll see that there are plenty of cases in which you would want to update the address of the Oracle. As an example, say there's a bug and the Oracle gets redeployed. What then? You have to redeploy everything and update your frontend. It's costly, time-consuming. So the way you'd want to go about this is to write a simple function that saves the address of the Oracle smart contract in a variable. Then it instantiates the Oracle smart contract so your contract can call its functions at any time. Put it to the task. In the box to the right, we've pasted an empty shell for the color contract. Declare an address named Oracle address. Make it private and don't assign to anything. So private comes first. Next, create a function called setOracle instance address. This function takes an address as argument. Oracle instance address. It's a public function and it doesn't return anything. First line should set Oracle address equals to Oracle instance address. Calling the Oracle contract. For the caller contract to interact with the Oracle, you must first define something called an interface. Interfaces are somehow similar to contracts, but they only declare functions. In other words, an interface can't define state variables. Constructors are inherit from other contracts. You can think of an interface as of an ABI. Since they're used to allow different contracts to interact with each other, all functions must be external. Let's look at a simple example. Suppose there's a contract called fast food that looks something like this, like the following. This is very simple contract implements a function that makes a sandwich. If you know the address of the fast food contract and the signature of the make sandwich, then you can call it. A function signature comprises the function name, the list of the parameters, and the return values. Continuing with our example, let's say you want to write a contract called prepare lunch that calls the make sandwich function. Passing the list of ingredients such as lice, to make it so that the prepare lunch smart contract can call the make sandwich function, you must follow the following steps. Define the interface of the fast food contract by pasting the following snippet into a file called fastfoodinterface.sol. Next, you must import the contents of the fast food interface sol file into the prepare launch contract. Prepare lunch launch. Lastly, you must instantiate the fast food contract using the interface. At this point, the prepare lunch smart contract can call this make sandwich function of the fast food smart contract. Putting it together, here's how the prepare lunch contract would look like. So you import, then you create an instance, and then create the function. I'm not sure if I understand really well. Now let's use the above example for inspiration as we set up the caller contract to execute the update if price function from the Oracle smart contract. So number one, imports. So I need to import this file. Declare its price Oracle interface. So this part I'm not really sure about. We'll go ahead and create a new file, place it into a new tab. Let's focus back on caller contract. After the line of code that declares the program import the file, let's add if price oracle interface variable named oracle instance. So I guess I should do like this. Instance. Paste it above the line of code that declares the oracle address variable. Let's make it private. Now let's jump to the set oracle instance address function. Instantiate the if price oracle contract using if price oracle interface. So it's the same thing that was done here, I think. So if price oracle. I'm not sure if that's what I'm supposed to do because I don't see any these anywhere. Maybe I need to put this function there. Store the result in the oracle instance variable. If you can't remember the syntax for doing this, check the example above, but first try to do it without picking. Alright, so it has to be the function here. Yeah, because it doesn't make sense to be the other thing. By now you probably know enough about Solidity to figure out that there's a security hole in this code. In the next chapter I explain how to make the set oracle instance address function safe. So it might be this. The function is public, so everyone can change the address. So it isn't this one. And I'm not sure I'm getting an error here. So import. So just the comment. Maybe I need to erase this comment as well. Oh, so maybe I have to put this here. It doesn't make sense. Or maybe is this? Yeah, I don't get it, actually. I didn't understand this explanation here. It's a little bit confusing for me. Maybe I'm getting tired as well, because I spent a lot of time already. So the interface should be here. This part that I don't understand. So you're calling the interface. So maybe just like this. And then I pass the Oracle address here. But it doesn't make sense because this just gets the price and returns a uint. Oh, there we go. I still don't get it really well. Did you manage to identify the security issue in the previous chat? Public function. The only owner function modifier is the solution. You must use something called a modifier. Import the contents. This is how using modifier looks like. Modify the code to import the contents of open Zeppelin. Make the contract inherits from is ownable. So is ownable probably has the modifier. Only owner. I think it comes before the specification there. Where is this? Fire new Oracle. I think it's event. Event. Then I don't really remember. Maybe like this. While you're here, you would want to fire an event so that the front end gets notified every time the Oracle address is changed. We went ahead and declared an event named new Oracle address event. The last line of the set Oracle instance address function should emit pass its Oracle address as an argument. So maybe it comes after the thing. Oh, I have to. Do I have to change? Okay, so now it works. So maybe here is a meet. No. Or maybe. Oh, okay. It is a myth. Using a mapping to keep track of requests. Way to finished off the set Oracle instance address function. Now our frontend can call it to set the address of the Oracle. Next, let's look into how the Ethereum price gets updated. To initiate an Ethereum price update, the smart contract should call the get latest Ethereum price function of the Oracle. Now, due to its asynchronous nature, there's no way the get latest if price function can return this bit of information. I'm getting tired. I think I'm probably gonna have to take a break soon. I do want to finish this today, though. So, what it does return instead is a unique ID for every request. Then the Oracle goes ahead and fetches the Ethereum price from the Binance API and executes a callback function exposed by the caller contract. Lastly, the callback function updates the Ethereum price in the caller contract. This is a really important point, so I spent a few minutes thinking about it before moving forward. Now, does implementing this sound like a hard problem? Actually, the way it works is easy. Just bear with me for the next 2 chapters. So, it calls the get latest if price. Function. So it returns a unique ID for every request. The oracle fetches Ethereum price from Binance API. Callback function updates the Ethereum price in the caller contract. But isn't this the same as relying on the Binance API to get the prices? So it kind of feels like it conflicts with the stuff they talked about earlier. Every user of your dApp can initiate an operation that will require the caller contract to make requests to update the Ethereum price. Since the caller has no control over when it will get a response, you must find a way to keep track of the pending requests. Doing so, you'll be able to make sure that each call to the callback function is associated with a legit request. To keep track of requests, you use a mapping called myRequests. In Solidity, a mapping is basically a hash table in which all possible keys exist, but there's a catch. Initially, each value is initialized with the type's default value. You can define a mapping using something like the following. Can you guess what this snippet does? Well, as said, it sets the balance of all possible addresses to 0. 0 because that's the default value for uint. Setting the balance for message.sender to some new value is as simple as this. Put it to the test. We've gone ahead and declared the myRequest mapping for you. So here. The key is an uint 356 and the value a bool. We've also declared an event named received new request at the event. Make a function called update Ethereum price. It doesn't take any parameters and it should be a public function. The first line of your function should call the oracle instance.getLatest Ethereum price function. So it's the function from the other file. Store the return value in a uint called uint256 called ID. Next, set the myRequest mapping for our ditch-bit true. The last line of our function should fire the received new request at the event and pass the ID as an argument. The caller contract logic is almost complete, but there's one more thing you should take care of. As mentioned in the previous chapter, calling the Binance public API is an asynchronous operation. Thus, the caller's smart contract must provide a callback function which the oracle should call at a later time, namely when the Ethereum price is fetched. Here's how the callback function works. First, you would want to make sure that the function can only be called for a valid ID. For that, you use a require statement. Simply put, a require statement throws an error and stops the execution of the function if a condition is false. Let's look at an example from the Solidity official documentation. The first parameter value is true or false. If it's false, the function execution will stop and the smart contract will throw an error. When sharp Once you know that the ID is valid, you can go ahead and remove it from the myRequest mapping. To remove an element from a mapping, you can use something like the following. So Just use delete and then specify the key, the value. Lastly, your function should fire an event to let the front end know the price was successfully updated. Put it to the task. We've gone ahead and declared a public function called callback. It takes two arguments of type uint 356, Ethereum price and ID. So it's this one. So it's outside of this function. After the line that declares a smart contract, create a uint variable called Ethereum price. Also, it's here. Called if price. Let's make it private. And don't assign a trinity. Create an event called price update event. So assume it's here as well. Price updated event. Takes two parameters. If price and ID, both parameters uint 256. Next, let's fill in the body of the callback function. So it seems like these events are really important because they are the bridge between the blockchain and the JSON stuff, the Node.js stuff. The function should first check to make sure request ID is true. User requires statement. I think by default it's probably gonna be true. So should be this request is not, and this. Next, save the new if price, the one that comes from the function parameters, into the if price variable. The function should then call delete to remove the current ID from my request. Lastly, let's fire the events. Price. I think I typed the wrong way. Yeah, it's supposed to be caps lock here. Price updated event. Oh, and it should be declared there. And then I'm probably gonna pass the ID, the price, and the ID. The argument should come from the function errors. This was a lot of logic to implement, but there is still something left out. Yeah, so I'm not sure. Can't be updated Ethereum price. Yeah, I don't know. So maybe I should be dot ID. Because it's a mapping. And then the emits wrong apparently as well. I'm gonna try the dot notation. It's done. It doesn't work. Yeah. No, so maybe that was the problem there. And probably not, because they are both giving me the flag. So maybe I need to put some condition here. Message.sender equals this. I don't think that's correct, but yeah. It said that the first argument should be this thing here. Is request statement. First parameter should be my request ID. Oh, so maybe it's the comment here. No. I don't get it. What am I doing wrong here? Yeah, forgetting something stupid. Like some typo or something like that. And the other ones I also don't know what's wrong with them. So what if I put this here? So that solved that one. What about these ones? Or maybe I'm using the wrong ID. Yeah, that's the problem. I didn't realize, actually. Did you figure out the answer? Before you wrap up the callback function, you must make sure that only the Oracle contract is allowed to call it. In this chapter, you create a modifier that prevents other contracts from calling your callback function. Do not delve into how modifiers work. Remember that you've already stored the address of the Oracle into a variable called Oracle address. Thus, the modifier should just check that the address calling this function is Oracle address. But how do I know? How do I know the address that calls the function was? Solidity message.sender is a special variable that specifies the. Okay, so it's probably gonna be require, and then message.sender is equal to the Oracle address. We're gonna tell you require. First line of code should use require to make sure. If not, it should throw the following error. You're not authorized to call this function. Remember, almost forgot to put this. Great job, you just finished implementing the Color Smart contract. Now it's time to move forward to the Oracle contract. Let's start by taking a look into what this contract should do. The gist of it is that the Oracle contract acts as a bridge, enabling the Color contract to access the Ethereum price feed. To achieve this, it just implements two functions, get latest price and set latest price. To allow the callers to track their requests, the getLatestIfPrice function should first compute the request ID, and for security reasons, the number should be hard to guess. What security reasons, you ask? In the third lesson, you're going to make the oracle more decentralized. Generating a unique ID makes it harder for oracles to collude and manipulate the price for a particular request. Yeah, that's the stuff that I was wondering about before. In other words, you would want to generate a random number, but how can you generate a random number in Solidity? One solution would be to let loose a zombie on the keyboard. The poor zombie will also type spaces and letters, so a random number like this. Even though zombies were hard, however, Solidity compute's good enough. The above takes the timestamp of now, the message to the sender, and incrementing nonce, a number that is only ever used once. So we don't run the same hash function with the same input parameters twice. Then it packs the inputs and uses CAC 356 to convert them to a random hash. Next, it converts the hash to a uint. Finally, it uses modulos to take only the last 3 digits. This gives you a good enough random number between 0 and modules. So it's doing the ABI stuff. Now message the sender and randoms. Lesson 4 explains why this approach is not 100% secure and provides. I feel like they've already touched upon this. Put it to the task. We've created a shell for if price. Oracle contract take quick browse through the code before continue. Note that your contract is zonable, and we've also included the content of the caller contract interface file. At the bottom of your contract, define a function named getLatestIfPrice. Should be a public function. So public returns uint 356. On the first line, use randoms ++ increment announce. Compute a random number between 0 and modules and store the result in a uint called ID. So it's gonna be CAC, that's 356, and ABI.encode packets, then now message the sender and randoms divided by modules. Oh, here has forgot the uint here. To convert into integer, an unsigned integer. So I think that's correct. If you get stuck, feel free to take a look at this example above or generate. Your solution should be similar. I shall to get function in the next chapter. So what's wrong? I need to return this, maybe. Oh, this I should be inside of here. And now I need to put another one here. Yeah, but I should probably be returning this as well. Maybe in the next one, it's gonna tell me to return stuff. It's okay, this is still not working. ID. Wins CAC 356. No message sender. Yeah, I'm not sure what's wrong here. Also, these modules should be outside of the thing. So maybe that's the problem. Yeah, there we go. Chapter 9, the get latest if price function. Good job, you've computed the request ID. Next, you would want to implement a simple system that keeps tracks of pending requests, just like you did for the caller contract. For this, you'll be using a mapping. This time, let's call it pending requests. So this is the mapping. The get latest if price function should also fire an event, and lastly, it should return the request ID. Let's see how we can implement this in code. So I'm inside the function. We're going ahead and define the mapping called pending request. The key is a uint, the random number, and the value is a bool. First, you want to change the pending request mapping for this ID to true. So pending requests ID equals true. Let's emit get latest if price event. You should pass following parameters message.sender. I need to specify probably. And uint true 56 ID. Finally, the function should return ID. So I don't need to specify. And this is not working as well. Did I write the wrong way? Oh no, it's requests with an S. Okay. I think I'll be right back. I'll go to the bathroom. Also, in this chapter, we're putting together what you've learned so far to write the set latest if price function. This is going to be a bit more complex, but there's nothing to be afraid of. I'll avoid big leaps of thought and make sure each step is well explained. So the JavaScript component of the Oracle, the one we will write in the next lesson, retrieves the if price from the Binance public API and then calls the set latest if price, passing it the following arguments. The if price, the address of the contract that initiated the request, the ID of the request. First, your function must make sure the that only the owner can call this function. Then similarly to the code you've written in chapter 6, your function should check whether the request ID is valid. If so, you should remove it from pending requests. Function sat latest if price price and viewing 356 ID. And then I need to put the modifier here. Which I forgot. Which one is it? Yeah, ownable. No. Only owner, I think. Let's see. I'm pretty sure it's only owner. Maybe only Oracle. Yeah, only Oracle probably. So I think it's only Oracle. Use require to check if pending requests ID is true. The second parameter should be the message, our message. If you don't know how to do this, revisit chapter 6 to refresh your memory. Remove ID from, so delete. We're going to continue defining this chapter. Pending requests. I think I wrote it correctly. So what am I missing here? So maybe I don't need to pass this. Delete, there's an extra space. And here maybe it's only owner instead. So maybe this comes before public. I never know if it comes or not before. It's probably after, because of the mistake he's giving me here. Yeah, so I'm not sure what's wrong now. It has to be this modifier here. And it's the only one that I have, so see color contract, so maybe it comes from this one. No, this is the inheritance stuff. I wrote everything correctly. Don't forget to make it so that only the owner could call it. Use required to check if pending request ID is true. Oh, it has to be underscore ID here. But it doesn't make sense because it says ID for the arguments. So I don't think that this is the problem. Oh, maybe it is, actually. Hmm. I don't understand though, why. So maybe here it has to be underscore ID? No. I think I'm just gonna look at the solution. No, it's the same thing. Oh, it's probably somewhere else the mistake. Oh, it has to be underscores here. It's weird because they put only underscores only on the first one. The set latest if price, I don't think it makes a difference. It's just probably for the way they did the tests there. The set latest if price function is almost finished. Next, you have to instantiate the caller contract instance. In case you forgot how to do this, or you need a bit of inspiration, take a quick glance at the following examples. Caller contract instance. So you call the contract with the name, and then you just make that equal to an instance with the address. With the caller contract instantiated, you can now execute its callback method and pass it the new if price and the ID of the request. Lastly, you'd want to fire an event to notify the front end that the price is being successfully updated. So caller contract interface. Caller contract instance. Then we make caller contract instance equal to caller contract interface. And then you pass the caller address probably. Initialize caller contract instance with the address of the caller contract. Just like we did with my contract instance above. Note that the address of the caller contract should come from the function parameters. Run the caller contract instance callback. So I need to put this dot callback, passing if price and ID. Emit the event. If price, caller, address. Okay. Oh, so there's still two more. I thought this was the. I don't know how can I say this. I thought there was only one more after this one. So I think I'll finish one more and then I'll take a break probably. Or maybe I'll stop talking so much, so just save your energy. In 2 hours and a half already. Oh, I should put a weight here. Just probably exactly like this. But instead, Oracle, Prism. Stational network ID. Yes, correct. Oh, I forgot to call it. That's the problem. Hey, Arisa, how are you? I think I'm gonna probably take a break now. Because I can feel that I'm already trying to rush things just so I can take a break. Because I'm tired. I think this one. It's probably the one that I should be. Yeah, I think I'm gonna take a break actually. While you're here, maybe I'll try to do this one and then I'll take a break. Let's make it so that your function also listens for set latest if price event. It works similarly to the above. The only difference is that since we won't be using this in this lesson, you don't have to do any processing. Leave the comment in place for now, this will be useful. Decide new functionalities. So copy and paste this one. Update the name of the smart contract. Also should be Oracle contract, I think. Plan save the name of get latest price event. I think this test might be a little bit too easy in order to retain the information. Replace the comments with a line of code that calls an async function named add request. Also this one. It takes one parameter. This should be function event, and of course you have to prepend await. So now I don't know what is await here. Maybe it's await instead of async. Yeah, I'm just gonna look at the answer. Also, get latest. Also, I should erase everything here. Oh, async function filter events tree. Yeah, so I should erase this part. Oh, I have to put the add requests here. And I need space here. What's wrong now? Also, there's no what? Oh, I need to put below this Oracle events salary price. It comes here. It's basically the same structure, but with a different for the different function. Probably mess up the thing here. Yeah, it's missing this one. So I am getting a mistake now. So I should return here. Yeah, that makes more sense. I think I'm gonna take a break. I'm already too tired. I'm probably gonna come back later today, try to finish this. Try to finish all the lessons, the 4 remaining lessons. Hopefully, I won't get too tired and have to stop. But yeah, so see you then.